In today's lecture, we're going to learn about curvature, normal, and tangent vectors. We're going to start off by talking about what curvature is and how circles can be used to indicate curvature at a certain point. We'll then talk about the principal unit normal vector and use the example of acceleration and the components of acceleration to tie together curvature, normal, and tangent vectors. Well, you're probably wondering, what is curvature? Well, curvature is the measure of the degree of curviness of a curve. That is, how sharp or rounded the curve is at a point. For example, let's take two curves. Here's one curve. Here's another curve. Let's pick a point on each curve. So let's look at this top curve and choose a point right about there. And let's look at this bottom curve and choose a point right about here. Visually, you could see for this top curve that this is a very curved point. Now for this bottom curve, you could see that this curve is very shallow. So at least looking at it visually, we have a good sense of what curviness is. We'd say that top curve on average is curvier than the bottom curve because the roundedness is more sharp on the top curve and more shallow on the bottom curve. Let's see if we could be a little bit more quantitative on what we mean by curviness. So to do that, let's look at the unit tangent vector between 2 points on each curve. So let's say let's go ahead and look at how the unit tangent vector changes with the arc length of a curve. Looking at the top curve, let's say we have a change in arc length. We could maybe measure our arc length from this point to the first point on our top curve. And then let's choose a change of arc length about that long. This will take us to our second point of the top curve. And I'll go ahead and identify this little segment as being associated with our change in arc length. Let's now look at two tangent vectors at the points we indicated in the top curve. So this tangent vector, let's make this a unit tangent vector. So I will define this unit tangent vector with this, and this occurs at the value of s in arc length. Now, a little bit of an arc length change later, we'll have a vector, a unit tangent vector of the same length. It's unit in length. And this will correspond to s plus delta s because we had a small change in our arc length. So let's take those two unit tangent vectors and look at how they change. So what I'm going to do is I'm just going to copy and paste each one so we could take a closer look. Let's move these down here. Well, in order to look at the change in the tangent vector, let's put these two vectors tail to tail. Now that we have these two vectors tail to tail, let's label each one. So this bottom vector, remember, was our unit tangent vector at the first point, and this more vertical vector is the unit tangent vector a short arc length away. Now the change in these two vectors is given by this third vector that connects them head to head. Let's label this as the change in the unit tangent vector. Now this change in the unit tangent vector, again, is just the final vector minus the initial vector. Because both of these vectors, because both of the unit vectors are unit in length, in other words, their length is exactly 1, the only way these two vectors can change is by a change in their direction. So in talking about the change in a unit tangent vector, it's really associated with the change of direction. And we could probably say that a curve is more curvier if it has a greater change in direction for a particular length of arc. So right now, we have this change of direction identified by the blue curve right here. So this represents the change in the unit tangent vector between the 2 points I've identified. Let's go ahead and I'm just going to go ahead and label these points 1 and point 2 because I want to look at a flatter section on this same curve. Let's look at another section. A section may be right here. Let's label this point, point 3. And let's choose the same change in arc length from point 3. So I'm going to take that first change of arc length from point 1 and 2, and I am going to approximate the same change starting from point 3. And that's probably about reflective of our original change of arc length. Let's label the end of that point 4. Let's now look at the unit tangent vectors at point 3 and point 4. So these unit tangent vectors, I'm going to sketch them to be the same length, 1 unit in length, and they're going to be tangent to the curve at the respective points. For point 3, the unit tangent vector is approximately like that. For point 4, the unit tangent vector is approximately like that. Notice there is very little change in direction between points 3 and points 4. Let's just go ahead and label this the unit tangent vector at point 3. We'll label this the unit tangent vector at point 4. And as a reminder, we will indicate the same change of arc. Well, let's find the change in the unit tangent vector between the 4th unit tangent vector and the 3rd unit tangent vector. And the way we could do that is to attach those two vectors tail to tail. Let's go ahead and copy them and use them visually to attach them tail to tail. Let's move these two down here, and let's attach them tail to tail. Okay, so the unit tangent vector T3 is right here. The unit tangent vector T4 is right here. The change in the two unit tangent vectors is drawn from the head of T3 to the head of T4. This right here represents the change in the two unit tangent vectors. So notice the change in the unit tangent vector from point 3 to point 4 is a lot smaller than the change in the unit tangent vector from point 1 to point 2. We could compare those magnitudes directly. Let's compare these two magnitudes directly. So we see that the unit tangent vector from 1 to 2, this is about 85 pixels in length. While the unit tangent vector from 3 to 4, wow, that's pretty small. That's only about 20 pixels in length. So if we look at that, again, the change in the unit tangent vector from 1 to 2 was approximately 80 pixels in length, while the change in the unit tangent vector from 3 to 4 was about 20 pixels in length. Now, visually, again, looking at this curve, it is clear from the curve that between points 1 and 2, that is a lot more curvier than points 3 and 4. Between points 1 and 2, it is more sharply pointed. Between points 3 and 4, it is more flat. And the change in the unit tangent vector for each of these segments kind of reveal that story. The greater the change from 1 to 2, the greater the curvature. The smaller the change in the unit tangent vector, the smaller the curvature. And the thing that we held constant for both of these was the arc length. So we said, and we see that the change in the unit tangent vector from 1 to 2 per change of arc length. And remember, we kept the arc length the same. I'll just write this for now. And this was greater than the change of the unit tangent vector from 3 to 4 for the same change in arc length, where we are saying that the change of arc length from 2 to 1, we kept the same as the change in arc length from 3 to 4. This means that we could use the unit tangent vector and how it changes with arc length as a measure of this quantity called curvature. This gets us to a definition of curvature. Let the position vector r be a smooth parameterized curve. If s denotes the arc length and t vector, that's a unit vector, is defined to be the derivative of the position vector over the magnitude of the derivative of the position vector, if that is the unit tangent vector, then the curvature of r is given by, now that thing that looks like a K, that's the Greek letter kappa. So kappa is what we use to represent curvature. So this is saying kappa, curvature, as a function of arc length is equal to the magnitude of the rate of change of the unit tangent vector with respect to arc length. So kappa, curvature, as a function of arc length is equal to the magnitude of the rate of change of the unit tangent vector with respect to arc length.